So we just saw that P0 is R0 to 1 times P1, and it turns out R1 to 0, which is the reverse of this, is nothing but R0 to 1 transpose, which is also the same as R0 to 1 inverse. But now we can talk about also having another transformation from P1 or 1 frame to 2 frame. Let's imagine a sequence of 2 rotations. So R1 to 2, P2. P2 is still the same vector, but expressed in terms of another coordinate frame with different orientation. Now it is obvious that if I wanted to look at the relationship between components along 0 frame and components along 2 frame, still the same vector, right? I can work out that relationship by simply plugging in this expression for P1 over here, and I would get P0 is equal to R0 to 1, and instead of P1 here, I plug in the whole thing here, which is R1 to 2, P2, and that tells us that multiplying these two rotation matrices together gives me the relationship between the 0 frame and the 2 frame. So this is again a nice property of rotation matrices. When you have multiple rotations involved, you simply have to figure out the individual rotations and multiply them together. But one thing to be careful here is this is a matrix multiplication. So if you reverse the order, the result changes. And it has to be in a specific order. So you remember this order, and that's something that can be very confusing. Setting up rotation matrices, remembering the sequence of rotations is something that remains confusing for a long time. Every time you set up a new robot, you will again feel like you are a little bit confused with this, but don't worry, you will be able to figure it out. Okay, so we were able to do multiple rotations as multiplication of rotation matrices. Now the task is, every time do we have to figure out all the unit vectors and dot products of all the unit vectors? The answer is no. We will use this fact that we can do multiple rotations and then multiply them together. So every general rotation, we will think of it as a sequence of simpler rotations. That makes this life a lot easier for us. So let's think of some standard rotations. So if it so happens that I have my blue frame as the 0 frame and my red frame happens to be just one rotation about the z axis by angle theta, which would mean that my z axis is still along the same direction. So my z0 and z1 are collinear, but I would get my x1 and y1 to be rotated but still in the same xy plane. So if I go ahead and write down x0, y0, z0, it would mean that this angle is theta, this angle is theta. They are still all in the same xy plane, and z1 is still along the same direction as z0, and this would be y1. Now in this case, you can go back and look at the rotation matrix expression and you can figure out all these dot products, but some of the things would be obvious. So k0 hat and k1 hat dot product would be 1 because they are collinear, right? So some of the, and then all the k's will be perpendicular to all the i's and j's, so those terms will be 0. So you can go ahead and have a much simpler expression for this rotation matrix. So this is called R about z by angle theta, because this is a standard rotation about axis z by angle theta, and this would end up You can work out the direction cosines. They are straightforward. You would get cosine theta minus sine theta 0, sine theta cosine theta 0, 0, 0, 1. This is how the rotation matrix will look like. So it's called standard rotation or basic rotation about z-axis. This makes life a lot easier because every time we are not working out the dot products. The minute we see there is a rotation about z-axis, we can blindly apply this expression. And as you would have guessed, you would have two more basic rotation matrices. You have basic rotation about y-axis by angle theta and basic rotation about x-axis by angle theta, and this would be cosine theta 0, sine theta 0, 1, 0, minus sine theta 0, cosine theta. And last one is basic rotation matrix about x-axis by angle theta, and this would be 1, 0, 0, 0, cosine theta minus sine theta 0, sine theta cosine theta. Now the good news is these are all the rotation matrices that you would ever need. Why? Because any three-dimensional rotation, you can always think of that as a composition of a sequence of rotations about x, y, and z axis. So you can think of a rotation like this as first you rotated a certain amount about the z axis, then you rotated a certain amount about the x axis, and so on and so forth until you reach the new configuration. Remember, the sequence of rotations is important. The other thing that can be very confusing, but let me reiterate again, is P0 is R0 to 1 P1, right? So if I take this example, I start with the blue axis, then rotate by angle theta, and I get the red axis, which is the 1 axis. So I think of starting with blue, then rotating, and I get this rotation matrix. But then this rotation matrix I have to multiply with the new coordinate, or coordinate in terms of the new axis, to get back the coordinate in terms of the old axis, the blue axis. So this is again, this sequence is something that can be confusing, so I'm just going over it one more time. The way you figure out this rotation matrix is you start with the original or the 0 axis, you figure out what rotation needed to be carried out to reach the configuration of the 1 axis, and if it's a basic rotation, you basically pick up one of these. But then the way to use it is you are always using coordinates in the 1 frame first, then multiplying it with the rotation matrix, pre-multiplying to get the coordinates from the 0 frame. Right? So remember this sequence. You figure this out by going from 0 to 1, then you take the 1, multiply it with this matrix to get back the 0. Right? So your computation is always kind of going back and forth. So this completes rotation matrices. You just have to remember these 3 basic rotation matrices, and then remember to imagine any arbitrary rotation as a sequence of simpler rotations, and just keep multiplying these matrices in the right order to get the relationship between the vectors.